What's up? This is Matt Brown. In today's video, we are going to discuss Binwalk version 3. That's right, the original author of Binwalk has come out with a complete rewrite in Rust, and it is fast. In today's video, we're going to compare it to the old Binwalk and just see how much faster it is, and we're going to talk about how we as a community can help contribute with beta testing as well as features and improvements. Let's go over to the repo now. And so you can see here on my screen that this is the Binwalk repo. If you haven't used this tool before, what Binwalk does is it is a tool that takes in a firmware file, or really any kind of file, and will attempt to peel back the layers of all the files and file systems contained within that initial file. And it is really intended to unpack firmware from IoT devices primarily, but you can feed it any kind of file and it will perform various levels of analysis. It'll perform entropy analysis. It will, like I said, it will look for all sorts of magic file bytes inside of the initial file that you feed into the program. Well, the original Binwalk was written in Python, and Python is great. Python is easy to write code in, but when performance is the thing that you care about, Python can leave you wanting something faster, and that's exactly the bottleneck that Binwalk ended up having. And its original author has seen this issue and is rewriting the project, has rewritten much of Binwalk already in Rust. And so you can see right here, we can see that Binwalk version 2, all of the old Binwalk is being depreciated, and Binwalk version 3 is being maintained here. And so we can click on that and we can see now that we're in the Binwalk v3 branch on GitHub. It still is in kind of a beta release, and you can see here him talking about it, that it's still considered unstable, experimental, but I have to say that for the most part, this tool is it gives me all the same information that the old Binwalk tool gave me. It just gives it a lot faster, and that is exactly what I'm looking for from a tool like this. I will sometimes deal with extremely large firmware dumps from eMMC chips. These modern eMMC chips can be 4, 8, 16, 32 gigabytes. And when you dump that entire chip and you use the old Binwalk tool to scan through it, sometimes it can take hours for it to complete. And so here we can see him giving some demos and boasting just how fast this tool is, but we want to actually take a look at this. So while I was getting ready and prepping for this video, he actually just committed something like 4 hours ago. And so he's got this new demo, and he has information about a Docker file installation. So we're not going to do that, and there's a couple reasons why we're not going to do that. One, I just like to compile things myself from source, but also in this video we are going to talk about a extra signature that I am looking to develop and add and contribute back into this code base. And to do that, I need to compile it from source, obviously. So, but if that's not what you want to do, if you just want to get this up and running really quickly, he does have a Docker image here, and he probably has all the extractors already installed. Now, again, for people that have used Binwalk, you've probably got all these extractors installed already. But if you haven't used Binwalk, Binwalk relies on a lot of external third-party software. So once it identifies a file system, let's say it identifies an ext4 file system or a squashfs file system, that's more like what you're probably going to find in an IoT device, then it relies on other tools to unpack those file systems. And so your machine needs to have those other utilities. That's not built into Binwalk, and that's true of the old Binwalk, and that is also true of the new Binwalk, Binwalk v3. So I'm assuming that this Docker file has all those dependencies already figured out for you, which will be a great thing if you're new to this. But we are going to do things the manual way here. So we're going to follow these instructions more or less. I run Arch Linux, so I can't apt install something, but I already have all this stuff installed. And then you can see here that you basically git clone, and then you use the Rust cargo tool to compile this software. And so you can see here that we're cloning this Binwalk v3 branch, and I have already done that over here in my shell. And so you can see here that we are inside of this Binwalk repository, and you can see that the branch we are on is Binwalk v3. You can see my other branch, which is a little bit of a hint at where we're going to go in the next part of this video. But first, I want to do a shootout between the original Binwalk and this new version that's been rewritten in Rust. It's supposed to be faster, right? So speed is something that we really care about here. And so what we're going to do is we're just going to open up another terminal here. We're going to make it big so you guys can see that. And okay, so the first thing we want to do is compile this, right? So we're going to say cargo build -- release. And so it's already compiled because I already did that, but you'll have to wait a little while depending on how much CPU resource you have, and it will compile the entire tool. And what it'll do is it'll drop that tool into the directory target release, and then there you see the Binwalk tool right there. So because I want to simultaneously have the old and the new Binwalk on my system, I'm not going to just straight up install this binary onto my system. I'm going to run the following command to symlink this newly compiled Binwalk to and make a symlink called Binwalk v3. That way, if I want to run the old Binwalk, I just run Binwalk, and then if I want to run the new one, I just have to put v3 on the end of it. So I already have that symlink installed, so that's how I'm setting that up, just so we know. And then we're going to go back, and then we're going to actually create that. Okay, so now I have 2 terminals up, and we are going to go into our test firmware directory where I have a number of pre-selected firmware samples that we can play with. So let's just start with something small and easy to work with. So from previous videos, you remember when the CB73, it was a camera that we looked at. We found a bunch of cool exploits in it. This is the firmware dump that I took from that camera. And so what we're going to do up here, we're going to do Binwalk v3, and we're going to see how fast that executes. And the cool thing about the new Binwalk is that it itself prints out the timing, again, because performance tuning was a big motivator in switching to Rust, and so that was clearly something that the developer of this tool cares about. So for the old Binwalk, it doesn't do that, so we're going to run the time command to see how long it takes here. And so we're going to do that same thing, and okay, it wasn't too bad. It was, it took 1.6 seconds compared to 55 milliseconds, right? So you can kind of see the time scale already of how different the speed is going to be. And this firmware that we just did that on is extremely small. It's only 8 megabytes. So when we step our game up to gigabytes of firmware data, it's really going to matter, as you can see. And we're not even going to wait around in some of these comparisons for the old Binwalk to finish. So now the next one I want to look at here is I downloaded this Raspberry. I'm doing some stuff with the Raspberry Pi. Cool, I've got this Raspberry Pi image here that is almost 6 gigabytes. So just a really big file to really see how fast Binwalk v3 is. So here we go. That's the wrong one. So we're going to do that, and again, I'm going to run this, but I'm not going to let this finish, because the thing about Binwalk, like I said, some of these bigger files, it will just go on forever. Now you notice something different. In this output here, we only get one file. And that's because Binwalk will, it will usually, especially when you do the extract. So we're not extracting, we're not doing the -E flag here yet. And so when you extract, there's the option with the -M flag. Let's take a look at this with the help menu. You can see here, if we do -E, then we can do -M, and then we can recursively try to extract and then extract and then extract files. The original Binwalk, again, part of the speed problem was with it was with just Python, right? Because Python's slower than Rust. But the other thing that it does is it tries to detect all sorts of stuff, and in the newer version of Binwalk, what the developer is doing under the hood, it's not even exposed in these flags yet, but he is developing it so that each signature has a confidence level, right? Of, you know, how confident am I in this signature? Like could it really easily be a false positive, especially in a large file with a lot of data? And so what we're going to see is the ability to tune things to get exactly the output you want with this new structure, which I'm really happy to see that. So I'm not even going to let that finish. Okay, so I just talked for almost 2 minutes while this ran, and if we remember, this one finished in 6 seconds. It scanned through a almost 6 GB file. It's almost scanning a gigabyte per second of data, which is really fast and really effective. So the last thing we're going to do is another large one, and this is going to lead us into the other thing that we want to do. So I'm going to start the slow Binwalk first, and I'm not even going to run the time command because we're not going to wait for this to finish, right? It could like these larger multi-gigabyte files would probably take hours to complete with the old Binwalk. That's how slow it is. So we're going to run. The next file up is Dishy. I wonder what that could be. So we're going to let old school Binwalk get a little head start here. New Binwalk is just kind of yawning on the starting line here, not worried at all. And we're going to run that. The other reason why I started the other Binwalk early is because I want to see one of the results. And it's not going to appear in the new Binwalk because a certain file type, a certain signature, I should say, has not yet been implemented. And that's what I am working on as we speak. Okay, cool. So here it took 17 seconds to scan through that file. We're getting some, ROM, FS file systems, very cool. Some device tree stuff. And okay, cool, I can stop. But there's something that, like I said, there's tons of false positive detections, and there's tons of these file types that I personally do not care about in the old Binwalk. So I'm happy that they're either not implemented or they're not activated right now. But one thing that I am very interested in is Lux or Lux. I don't know how you pronounce that. Tell me in the comments. But the old Binwalk found a Lux partition. So if you're not familiar with what that is, it's the Linux Unified Key Setup. I don't even know what it stands for usually, but it's a encrypted partition, and it's the most in Linux. It's the most common way to create an encrypted disk partition, and so the old Binwalk detects it, but the new Binwalk does not. So I have been working. So now we can close out old Binwalk. We're done. I'm done with it. Let's clear this out and let's go back to Binwalk. So I am going to check out a new development branch that I've been working on. And you can see here, it did not. Why are these going to? Oh. It seems to think. Why are these untracked files? Oh, well, all right. So we need to delete them. Don't know why they exist here. And now we're going to check out my changes. Cool. And now I'm going to recompile. So we're going to do cargo, build, release. Part of this is to make sure that it compiles correctly. Okay, yeah, I'm getting a bunch of warnings because my code is crap and I'm really new to coding in Rust, but it finished. So now I just want to show when we go to the test firmware, Binwalk v3, dishy, we're going to see now that it is able to detect our new partitions with my new code. And we'll look at the code a little bit, but it's nothing great. Not yet, at least. So here you can see that it has detected 3 encrypted partitions at the end of the firmware file now. So this is really helpful for me, but I want to do more, because here all I'm doing now is just detecting the existence of it. And you noticed in the old Binwalk, that's what it did too. It just detected, hey, I found a Luke's, magic. I found the magic bytes, and it would decode the hash. It would decode the hash algorithm that's being used. But that's it. And you'll see here, I have one such partition here. And when we're on the file command on this file, if I can do that without typing incorrectly. Oh, that's completely the wrong one. Here we go. And let me get that up there so you guys can see it in the video. So you can see here that when we run the file command on a Luke's partition, that there's tons of extra metadata inside of the header that it is able to parse, right? And if you're familiar with the crypt setup tool, we can do that with this as well. We can dump a Luke's partition, and we can get all this interesting data about it, right? We can see, the metadata area, the key slot area, and then we can see, information about the different data segments. And so this is all really interesting information, and this is information that Binwalk could automatically output when it detects. It could parse the header. It could not just detect the header. It could parse the whole thing. And so that's what I want to do in the future with my code. But I will show you if you guys are interested. So inside the source directory, I basically added 2 main source files. So the one is in signatures, Luke's, and here I've added this file. By the way, completely just copied the code from the ELF detection module, and then kind of made all the changes that I needed to, and deleted a bunch of stuff, right? So here we can see the magic bytes here. So all Luke's partitions are going to start with LUKS and then these 2 magic bytes, right? And so that is what is identifying. It's scanning through every part of the file, and then if it sees those 6 bytes in a row, it's going to say, hey, I have found a Luke's header. And so then it calls this parsing function, and then it also is going to call this parsing function, and it needs the parsing function to succeed. Well, I right now am not really doing a proper job of parsing this. So this is in structures where this is defined. So all I do is I just blindly return OK, right? And see, the whole idea is that this is a way to get rid of false positives, because if you just randomly had those 6 bytes in your file for some reason, but it wasn't actually a Luke's encrypted partition, then when you parse the rest of the header, if there was any kind of parsing error, it can return this error and it won't identify it. And so this is another huge improvement with Binwalk version 3, is that all of the magic byte stuff, the old Binwalk used this kind of extension to the file magic protocol, which is basically a config file that defines a way to identify a whole bunch of sections of a file header. And so by changing it to be completely implemented in code via these detection methods in the signature and the structure kind of subdirectories here, it lets you have a lot more fine-grained control, and it makes it a lot easier when you're developing a signature, right? You can just use code to decide if it was correctly parsed or not. So that is my code. I want to thank you for watching this video. I'm hoping to learn some more Rust, and if you want to learn more Rust and you want to contribute to this project, I highly suggest that you go over to the Binwalk repository, you compile it as a developer, and give it a shot, and look for things and just try to use it to scan your firmware, to extract firmware, and find bugs and report them. Thank you, and have a good day.